All right, let me speak about Cramers Rule, which is something every engineer should know.
What rule?
Cramers Rule. Cramers Rule. Now let's go back to the system of equations. I'll be very abstract, using variables rather than a concrete example. dx plus dy plus df gx h okay, and let's call this L and N. Now here, I doesn't mean the imaginary number I is a constant, and E doesn't mean the 2.7 something. I'm just trying to come up with regular, just some variable names. Okay. Now, what would this become if I change this in matrix form? First, what should I write? A, B, C, D, E, F, G, H, I. First, you write down the matrix of coefficients, and then what do you multiply?
X, Y, Z.
X, Y, Z. A column vector of unknowns. And just check that this times this does give you this very first one. Okay. Equals to what? L. How do you solve this? It will be simply the inverse of this matrix. That's how you solve it, technically. But you see, we just figured out how to get this inverse, and it wasn't easy. We had to do two things, right? Find the determinant, and then find the adjoint, and we had to divide the adjoint by the determinant. So it was a rather long process. So it's easy to write, but basically useless in computation. So what Cramer did was he looked at this and thought about a way to package this in a simpler way. Okay. So let me try to explain that part. How Cramer packaged this in a nicer way. Okay. It looks nice, but it's useless. It's too hard to use. Okay. So let's think about the following. First, write down what's. So we're going to call D as the determinant of that coefficient matrix. And then write down the adjoint of this matrix. A, B, C, D, E, F. And when we do that, we will, yeah, I guess we can write a lot, but, okay, so what should be in here? The very first one. It'll be the determinant of what? Yeah, it will be this one, right? You delete this element, you have to take E, F, H, I. And then if I delete this one and I get D, F, G, I, but because of the transpose, that actually comes over here. So it's D, F, G, I, okay, with the minus. Okay. Yeah, but what goes here? Can anyone tell me what goes here?
D. Oh, you want?
Yeah. So yeah, you're right. You delete the D. So what goes here?
E, I.
B, B, C, H, I. Put a minus or not?
Minus.
Minus, yes. Okay. Now what goes here?
BC.
BC,
EF.
EF. Okay, so, and then some more. I don't even know it right. But definitely this. So, do you agree with this so far?
Yeah.
Okay. Now, I know that 1 over d times this, let's just call this, this matrix as n. 1 over d times n is A inverse. This A inverse, where usually this matrix is called A, that matrix is called B. So this is A inverse times the B matrix. And so we can actually compute this now using that formula just for x. So let's try this. So xyz is now 1 over d times this matrix n, because that's the A inverse, times LMN. And this n is that matrix, right? I'm just going to write down the very top. And something here, I don't know. And then I'm going to multiply L and all right. Now, whatever you multiply this times this will be the value of x, right? Once you divide by d. And then to get y, you would do this times that and divide by d. The last one, this times that and divide by d. Yes?
Where you roll 1d n equals a, the inverse of a,
Hmm?
do you also need the inverse of d since we gave it the value d?
No, so you have to divide the adjoint by the determinant to get the inverse of the matrix.
Yeah, but then we give the matrix the value d. Or did we not? For the
Matrix is not d. The determinant of the matrix is d.
okay.
There's a difference between the matrix itself and the determinant of the matrix.
Yeah, because it says D equals A, B, C, D.
Yeah. So here, this bar means there's this. You have to distinguish between a bar, which means the determinant of the matrix, okay, and just parenthesis, which means the matrix itself, okay. That's a very important distinction, okay. This is a number. It's not a matrix. This is a number. And these are all numbers. These are not matrices. These are numbers. All right. Yeah, it's confusing. Okay. So if I multiply these two, I get x after dividing by d. So let's write down x. It's 1 over d times what times what? L times EFHI. And then minus n times BCHI. And n times BCEF. Right? Plus. Again, this is a number, not a matrix. Okay, these are you do BI minus HC times M, so that's a number. These are all numbers. Okay. Okay, so here we are, almost there. So Cramer looked at this and thought, well, this looks awfully lot like a determinant of something. So he tried to reverse engineer this. Okay, so you guys have to do that at some point, right? In engineering career, you sometimes have to look at something and try to figure out what was there before. So we're trying to reverse engineer. And after some thought, he reverse engineered it and said that this thing inside is basically the determinant of the following matrix. It's LMN with B, C, E, F, H, I. So let's think about why. So first, see, A, D, G are missing here, right? Yeah, A, D, G are missing here, right? Exactly. Yeah. So, and then instead of where A, D, G are there, there's L and N there. Okay. So his thinking was, well, maybe we should try the same matrix, but with L, M, N replacing A, D, G. Let's see what this gives you. It gives you the exact same thing as that one. So that's the amazing part. Okay. So if you actually did the column expansion of this, you can see that when you take L, it will be times EFHI, right? And then you take M minus BCHI, and plus N times BCEF. It's exactly the same as that one. And after that, you get an amazingly simple formula for X. See, once you realize what you have here is the determinant of this, then you get an amazingly simple formula. Let me just erase this one. An amazingly simple formula, which says simply, if you had this question, then your value of X is L, M, N replacing the first column, B, C, E, F, H, I, and then you divide it by the determinant of the original one. So that's Cramer's rule, Cramer's formula. Now, once you see the beauty of this formula, then you can almost predict what y would be. What would y be?
Just put LMN into the next column.
So A, B, C, D, E, F, G, H, I, divided by A, B, C, D, E, F, G, H, I. What was Z equal to?
Just move it over again.
Yeah, move it over again. So A, B, L, M, N. A, B, C, D, E, F, G, H. Now this is like 10 times better than actually trying to find the adjoint, dividing by the determinant, and multiplying out. First, it does, if you look at it, it does reduce the amount of computation you actually have to do. And it's very symmetric so that it's not hard to memorize. Cramer's rule is extremely easy to remember. And this is actually equivalent to knowing the inverse of a matrix too. So you can, another way to look at it is you can use these formulas to actually find the inverse of a matrix if you have to. So in some sense, it's better than finding it. All right, so let me talk about its uses. When you are trying to solve matrices when you're trying to solve system of equations by using matrices, there's actually an easier way, which is called reduced row echelon form. So there's something called reduced row echelon form called RREF, and most calculators, I mean TI-85, TI-83, TI-89, and TI-Inspire, these graphing calculators, they provide this functionality. So, if you had explicit numbers, okay, and you were to use matrices to solve such a system, what you're going to do is you're going to punch in this 3-row by 4-column matrix into your calculator, and there's a functionality called RREF to solve it. Okay, and that's actually the easier way to do it. Okay? I actually have some videos about how to do it, so you should watch those videos for your future class, since especially when you're doing circuits or when you're doing statics, these computations often end up with lots of variables, with lots of equations, and you can't solve them by hand. You really need to use your calculator, and the way you do it by your calculator is by using this. And because this is much easier than Cramers Rule, you would want to use this. Occasionally, by the way, if you want to do this, find REF by hand, the name for getting something is called Gauss-Jordan Jordan process. So if you do Gauss-Jordan, then actually Gauss-Jordan elimination. So if you want to do this by hand, you can search this up on YouTube. There's some very good videos on it, so you should do it. Okay? Now, however, there's a limitations to this method. The limitation is if your coefficients are not numbers, if it's given as some generic variable, then you can't do this. So what do? Then you use this Cramers Rule. So let me give you an example. In some cases when you're solving statics questions, this capital M, small m or capital M is mass of some object, and mass times, and then you end up with some acceleration because that's the force. So mass times x is some acceleration of something, and then you end up with equations for them. So let's say you have mx, m plus m, z equals to 0. Of course, in your statics context, there will be acceleration of one object. This will be the acceleration of the third object, so it will be a subscript 1 and a subscript 3. But let's just use x, y, z so that it's easier for us to follow, okay? So you have x minus y plus capital MZ equal to 0, and capital My plus z is equal to 1. Usually this will be the force F in some cases. Right? But definitely when you're solving statics question, you can have a system of equations like this, where you have x, y, z as unknowns, and because it's involving two masses, small m and capital M, you have to solve the system, but it's just too complicated to be solved by hand because it's like it's very confusing, right? Now this is where the Cramers Rule comes up. You use this formula. Let's see how this is applied. First, we have to find the determinant of this matrix. So let's see what is the coefficient matrix here. It's m plus, no, this is 0 because there's no y. 0 times y, and then m plus n. 1, negative 1 m, 1, negative 1 capital M, 0, m, and 1, right? 0. Okay, now let's do the row expansion, and that gives you m times negative 1 m1 plus m plus m 1, negative 1, 0 m This gives you negative 1 minus m squared times m, so that's what it is. This one is just 1m times this, so it would be m plus m and m, which is negative m minus m squared plus m plus m squared. Okay. Let's write the positive ones first. M squared plus m minus m minus m. So that's the determinant of the coefficient matrix, which will be present in all the denominators, according to Cramers Rule. Okay? Now, how do you get x? 0, 0, 1, right? To get x, you would replace the first column by matrix B, right? So we replace the first column. Now, we have to calculate the matrix of this, but then the easiest way is to go this way, because this has 2 zeros. I guess this is still okay, but let's do it this way. Then it's just 1 times the determinant of that, which is very easy to calculate, right? 0 times m is nothing, minus negative 1 times that, so what do you get? M plus m, m plus capital M. So this gives you m plus capital M, which gives you x equals to m plus n over m squared plus mn minus n minus n. How about y? The second row will be 0, 0, 1 for y, right? And m 1, 0. And we take this away, it will be m times m minus m. So it will be m minus m minus m over the same thing. But this time, I have to say that because of the checkerboard of signs here, this will have a minus. That will be y. And finally, for z, these will be 0, 0, 1, and that has to be replaced by 0, negative 1, and capital M. And when you choose this, it's this times that, so it's negative m. So z is equal to negative m over m squared. Okay. So if you use the Cramers Rule, I mean, to really appreciate this Cramers Rule, you should try to solve this without using the Cramers Rule. See if you can solve this for z and then plug it to the other ones and try to solve this with the system. That's going to be fun. Yeah. So if you do that, then if you get these complex answers, then you have to think about how great these formulas are. So often, I mean, in differential equations, sometimes you have to solve equations like this where the coefficients are sines and cosines. So if the coefficients are very complicated, then you want to use this thing called Cramers Rule.